If you want to spend any amount of time studying materials, you'll need to get comfortable with solids. You'll probably recall from grade school science that matter is solid when it fulfills the two requirements of having a set volume and a relatively fixed shape. That's a broad definition that accommodates a lot of dissimilar stuff, so it's useful to group solids into categories. Solids can be grouped by similarity in properties or classified into material families, but these useful categorizations are a discussion for another time. Instead, we're going to zoom down to the smallest scale and build materials from the bottom up.
A solid is considered crystalline if its structure is composed of atoms organized into a repeating three-dimensional pattern. You can think of a crystalline solid like a brick wall, where every brick is uniform and connect to create long-distance order. The brick is to the wall what the unit cell is to the crystal, the smallest repeating component that collectively make up the structure. Keep in mind that uniform orientation is not a requirement for a solid to be considered crystalline, so long as the unit cells are the same. This structure would also be considered crystalline. If all the unit cells happen to align, the material is termed a perfect crystal. In contrast, amorphous solids have a haphazard structure, where atoms are connected at random. Glass is a well-known amorphous solid, so much so that glassy has come to be used interchangeably to mean amorphous. The difference in structure between a crystalline solid and an amorphous solid results in different properties. Even though silicon glass and quartz are composed of silicon dioxide, and if you have an identical quantity of each atom, they are not interchangeable. If your quartz crystal in your watch broke, you can't just cut out an identically sized replacement from your window pane and expect your watch to keep time, because quartz is piezoelectric, while glass is an electrical insulator. Amorphous materials coexist with crystals across many families of materials. Some crystals can be identified at a glance. Others are less apparent. It's not immediately evident, for instance, that a metal spoon is crystalline. Identification sometimes requires lab equipment, such as an X-ray diffractometer. It can be overwhelming to consider many atoms in three-dimensional space. Fortunately, nearly every property of a crystal can be determined by understanding a single brick in the structure, like how many properties of a forest can be understood by a keen grasp of the characteristics of its primary tree. There are 14 types of unit cells, but today we'll be covering just 4 of them: simple cubic, body-centered cubic, face-centered cubic, and hexagonal close-packed. Of the pure elements solid at room temperature, a sizable portion have one of these 4 crystal structures, along with innumerable compounds.
Why does this matter?
Sorry, what?
Why is this worth my time?
Okay. Well, the unit cell tells us how solids form and how they break. It holds the key to millennial-old questions like, why does iron become steel, and why does tin disintegrate in the cold? Unit cells are integral to research on the cutting edge of modern materials. A material scientist without understanding of unit cells is like a doctor with no understanding of human cells.
Trial and error experimentation may yield accidental breakthroughs, but is the knowledge of fundamental structure that gives unmatched predictive power.
The first type of crystal to examine is the simple cubic structure. The hard sphere model is artistically complicated, so we often use the reduced sphere unit cell as a stand-in. This simplification is far easier to draw and makes it easier to identify an atom's neighbors in space. But keep in mind this model makes the structure look far more spacious than it actually is.
The simple cubic structure is formed by stacking atom layers directly on top of one another. If you drew a line through each row of atoms, you would have a perfect checkerboard. The unit cell cuts through the center of each atom as shown. 1/8 of an atom occupies each corner of the cube. The remaining 7/8 of each atom are contained in the neighboring unit cells. With 8 corners in a cube and 1/8 of an atom in each corner, a simple cubic unit cell has 1 full atom within it. A note of caution. It's easy to mistake 1/8 and 1/4 atom segments, probably because 4 1/8 segments make a full circle, but only half a sphere. Adding up atom segments may feel trivial, but it is deceptively tricky, be it forgetting how many corners a cube has or some other mental misstep. My advice: act under the assumption that your brain is actively plotting against you and will try at least once to trick you. It pays to double-check your intuition. Not only did I miss points on the midterm when I was in your shoes, but I also had to redo slides 2 times on this very video for the same reason. It might be worth your time to sketch up a quick key on the margin of your test for reference. Pretending for a moment this is an empty cube. How would its volume be determined? The volume of a cube is length times width times height. Because length equals width equals height in a cube, we'll set that value as a. Volume is a cubed. Having a volume of a cubed doesn't mean much unless it's anchored somehow to the real world. This is accomplished by noticing the side length is exactly 2 atom radii. Replacing a with 2r, the empty volume comes out to 8r cubed. With a quick internet search, you can easily determine the diameter of a particular atom, which then can be applied to our equation to yield the volume of that atom's unit cell. What if you were asked to find the volume of atom within this box, aka the occupied volume? At first glance, this appears like it will require some gnarly geometry, but it doesn't. Remember how the atom fragments could be sewed together into a single Franken-atom? That's simply a single tiny sphere, and you've been looking up and subsequently forgetting the equation for the volume of a sphere for years now. I'm going to introduce a new term here, and it needs to be present in your notes on each of these crystal structures. It's called the atomic packing factor, or APF for short. Mathematically, the packing factor is equal to the occupied volume of a unit cell divided by the total volume of the unit cell. In layman's terms, it tells us how much of the cell is occupied by stuff. Using the macro scale, for example, suppose you are moving into a new apartment and the rooms are as of yet empty and echoey. Ignoring closet space, this room has a total volume of length times width times height. None of the room's volume is occupied. The packing factor will therefore be 0. After unpacking your things, about 15% of the room is occupied. The occupied volume is 1.5 of the original volume. Plugging the values in, the total volume term cancels and gives a packing factor of 0.15. Now suppose you cram every available nook and cranny with stuff. Short of compacting the junk into a single solid block, the packing factor will still fall short of 1 owing to gaps between the items. This is important to recognize. Determined to reach maximum capacity, though, you mix up a batch of concrete and fill the gaps. At the cost of everything you own, the occupied volume is at last equal to the total volume, earning you a packing factor of 1 and probably a segment on the local news. Nature likes to pack solids tight, but when you are working with spheres, there will always be a substantial amount of space that goes unfilled. If your atoms aren't spheres, you should probably get that checked out right away. Unlike your room, there is no concrete that can fill these subatomic spaces. Even when smaller atoms rest in these spaces, there will still be voids that go unfilled. If you want to see how to apply the packing factor to give you an unfair edge in winning M&Ms, check out my other video. Returning to the simple cubic structure, our formula informs us that the unit cell has an atomic packing factor of 0.52. A hair over half the unit cell is filled with atom, with the remainder being empty space. This is pretty vacant for a solid, which is one of the reasons simple cubic is rare among the metals, with polonium being the only pure element that prefers this structure at room temperature.
One last aspect before moving on from the simple cubic structure. How many atoms does each atom neighbor? I'm not fond that science has decided upon the word neighbor in this context when touching is a better descriptor. Let it sink in that neighbor and touching are completely interchangeable. If an atom has 6 neighbors, it means it physically touches 6 other atoms. You might assume that this orange atom neighbors this green atom, and you'd be correct, because the 2 atoms physically touch. These 2 atoms look rather neighborly, but they are not neighbors because they do not touch.
To find the number of neighboring atoms, start by picking any atom. It does not matter which atom you choose in any crystal structure, it will always come out to be the same number. I've chosen this one. The atoms that touch it are as follows. 3 are within the cell's own structure, with a 4th located to its right, a 5th in front, and a 6th above. In the simple cubic structure, every atom touches 6 other atoms. To prove these really do touch, here is our atom with the touching atom fragments drawn in, and here are those atoms as spheres that I have numbered. Okay, that was a long while on simple cubic. Let's move on to body-centered cubic. This unit cell kind of reminds me of one of those puzzle boxes with the wooden ball trapped in the center. The BCC unit cell begins formation with the same type of layer we saw in the simple cubic structure, but every subsequent layer of atoms is staggered to nest in the spaces provided by the lower atoms. Drawing the boundaries demonstrates why a whole atom is contained in the middle of each of these cells. Notice that the BCC structure is just the simple cubic structure with an atom on the inside. We already determined the simple cubic structure has 8 1/8 segments. Add one whole atom and we find there are 2 atoms in each BCC unit cell. Determining the volume of the unit cell begins the same way, by setting the side length equal to A. Immediately, however, we encounter a dilemma. The side length is not 2r, but contains a gap of unknown size, like the smile of a child wishing for their 2 front teeth. Fortunately, geometry offers us a solution. It is possible to draw a line through the inners of the cell where the atom segments touch without any gap. Represented in 2 dimensions, the segment has a length of 4r. A segment of this kind that passes through the center of a cube to connect 2 vertices is, appropriately enough, what geometry calls the body diagonal. It is related to the side length A through trigonometry. Since we already know the body diagonal has a length of 4r, we can set it equal to the cubed root of A and solve for the side length of our cube. The side length is equal to 4r divided by the square root of 3. It's always a good idea to compare your results to your predictions, and recall that we said that the side length should be a little longer than 2r with the gap included. If you plug this into your calculator, the side length turns out to be 2.3r, which is quite close to what we predicted. All that's left to do is plug it into our equation. If you determine the number of atoms, finding the volume of the unit cell occupied by atoms will always be easy. Just multiply the equation for sphere volume by the number of atoms. Plugging in the values we've already determined, r cubed will cancel and leave us with 0.68. The BCC unit cell with 68% of its volume occupied is substantially more dense than the 52% of the simple cubic. This is one of the reasons why it is more prevalent, being notably favored by iron, and therefore steel, at temperatures lower than a furnace. As a helpful tip, if the radius doesn't cancel out when you go to find the atomic packing factor, you can be sure there was an error in one of your 2 volumes that you should go back and correct. When determining the number of neighboring atoms in BCC, it is easiest to choose the center atom. Every corner atom touches the center, totaling to 8. Easy enough. Will this still hold true if you picked a corner atom? Having 8 neighbors will hold true no matter which atom you pick, but this was not intuitive to me as a student, so I'll demonstrate it to you. First, the corner atom touches the center atom. Recall that atoms in the BCC structure rest in the spaces provided by the lower layer. This orange atom is held by 4 green atoms in a 4-leaf clover shape, one of which happens to be the center atom we already counted. In addition, another 4 atoms will lie atop the orange atom. When these remaining 7 atoms are drawn in, notice that our orange atom could just as easily be seen as the center atom in a BCC cell formed by these 8 green atoms. But hold on, what about these 3? Wouldn't that bring our total up to 11? Remember that neighbor is synonymous with touching, and none of these 3 touch our atoms because of the gap, no matter how neighbor-like they might look with the connected black lines. Face-centered cubic structure. This crystal is once again intuitively named by having an atom located at each of the 6 faces of the cube. When I go to draw the reduced sphere model, I always think of those magician trick dice where every face is a 5, but that's just me. Once again, the unit cell can be thought as a simple cubic structure crammed with a lot of stuff in the center. We can write this down as 8 1/8 pieces. The remaining atom fragments are 1/2 segments, and there are 6 of them, 1 at each face. This makes a total of 4 atoms in each FCC cell. Finding the volume of the FCC unit cell will be complicated again by that same gap between the corners, but fret not. There is no kooky line through the interior, but instead a crisp diagonal across the face. Trigonometry tells us the relation between the face diagonal and A. This diagonal has a length of 4r and can be substituted in the relation. Occupied volume is determined the same way as the previous 2 crystals. Plugging in the values into the atomic packing factor, we arrive at the tightest crystal structure yet and the upper limit of how dense spheres can be crammed. This maximum value will also be shared by the hexagonal close-packed structure, with these 2 belonging to what we call the close-packed family. FCC includes aluminum, nickel, lead, copper, and gold. When determining the number of neighbor atoms, I found it convenient to choose an atom on one of the faces. This atom touches the 4 corners on its face, as well as the 4 closest face atoms in the cell, for a local total of 8. The cube that lies directly in front of it supplies neighbors 9, 10, 11, and 12. Drawing these directly onto the cube leads to an unsightly and confusing mess, so I hope you can see how the second drawing of the orange atom would fit together. Simplifying the geometry further, the face atom is surrounded by a square of neighbors in the same plane, with a diamond of neighbors coming out of the plane and a second diamond of neighbors behind. For those of you like me who are challenged by picturing 3-dimensional space, it might be helpful for you to go back and watch this a few more times if you need. I'm not going to go through the more difficult scenario of starting with a corner atom, but it also comes out to 12. You may have noticed I didn't talk about how FCC is geometrically formed, but no, I didn't forget. Because FCC and HCP arise from the same initial stacking, it's just easier to talk about them together. Close-packed structures have atom layers that are staggered, in contrast to the grid shape of SC and BCC layers. This changes the quantity and shape of the pockets formed by the layers. The second layer is also staggered. This is where the paths divide. In the face-centered cubic, the third layer C is neither a repeat of A or B. This gives it an ABC-ABC pattern. In contrast, the hexagonal close-packed alternates between A and B and goes AB, AB, AB. We're going to talk more about the hexagonal in a moment. Before moving on, there remains one question. Where is the cube? You won't find it by cutting straight down, and you'll need more atoms. For clarity, I've hidden the remainder of the green and blue atoms that make up the second 2 layers. The cube can be found as thus. If you still can't see it, some molecular surgery might do the trick. When I took this class, this tilt caused me a considerable amount of distress. I couldn't see where the FCC had come from, and the 3D geometry hurt my head. I imagined that, as a metallurgical engineer, I would be regularly presented with photos of atoms and be expected to identify them immediately, like some kind of atom version of a birdwatcher. In case any of my viewers have this weird anxiety, there are 2 reasons not to concern yourself. First, you'll probably use an XRD to analyze the structure, which will spit out data that tells you the type of crystal. Second, even if you are looking at the image of the structure, the angle you view it is completely arbitrary, so you can just rotate it in a way that you can easily see the cube. So, no sweat. Bear with me, because this is the last crystal we're analyzing in this video, the hexagonal close-packed. There's just no easy way to box this one into a cube, so we're going to have to endure the weird geometry. The outer edge segments are 1/6 of an atom, and there are 12 of them in total. These 12 encircle the 2 half-atom fragments, one on the top and the other on the bottom. Lastly, there are 3 whole atoms that are sandwiched in the center. When sutured together, this comes out to 6 atoms per unit cell. So far, we've relied on A cubed to try to find the volume, but this is not a cube. We set A equal to 1 of the 6 sides of the hexagon, and we can see that that's equal to 2r. Your instructor may or may not have had you use trigonometry to figure out the area of the hexagon, but the equation is easily available online. Plug in the predetermined value of A and you will have the area of the crowning hexagon. To move on from area to volume, we need to multiply the height of the unit cell, C, by the area we already determined. We don't have a fancy geometric trick to find the value of C, so for now we'll accept this as the general equation for the volume. Finding the occupied volume is no different from finding it for the previous 3, though it will come out to the greatest magnitude from the 6 atoms in the cell. Without a value for cell height C, there is no way to find the atomic packing factor and verify if HCP shares the same packing value as the face-centered cubic. In the ideal HCP cell, however, a relationship between C and A has been experimentally determined. It also turns out that the vast majority of HCP structures are ideal, so unless you're working with one of the exceptions, you're free to use this relation. Rearrange C to isolate it and plug in the value of A. Drop the value for C into the equation for the unit cell volume. Sure enough, it comes out to be identical in packing to the face-centered cubic. Okay, prepare yourself mentally because the odd geometry of HCP makes it a real slog to get through in finding neighbor atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. HCP snatches up most of the remainder of the metals not taken by BCC and FCC, including titanium and zinc. Thank you for watching, and best of luck on your exams.